I think I can start introducing today's speaker, who's Professor Volker Springel, who's the head of the numerical astrophysics group at the Max Planck Institute for Astrophysics in Munich. He has been leading the world's largest simulation of the universe, addressing the growth of large-scale structures and investigating the role of dark matter and dark energy. He made major contributions to the understanding of the growth of galaxies. He is the member of the German Leopoldine Academy of Science, winner of the prestigious Gruber's Cosmology Prize in 2020, and has been awarded one of Germany's highest research awards, the Leibniz Prize, in 2021. And actually, looking at your CV, I've seen that you're starting getting prizes from your early age, and you have been consistently receiving prizes all along your career. So, Volker, please start.
Yeah, thanks a lot, Monica, for this nice introduction. And it's a real pleasure to be here with you, even though remotely. And speaking to CERN audience is giving me a little bit of a chill. I think you are obviously, the mecca of physics, and it's an honor really for me to speak to you about a subject that I suppose is a little bit far away from the work of many of you, cosmology and galaxy formation. That's what I would like to introduce in my talk to you. In particular, the work we are doing with large supercomputers in trying to understand nonlinear structure growth. So what I'll try to do this afternoon is to tell about dark matter structures on different scales, about hydrodynamical simulation of galaxy formation, and then about the importance of supermassive black holes for galaxy formation. And if time permits, maybe venture a bit in magnetic fields and cosmic rays, but probably this won't be enough time to this afternoon for this. So you have all seen images like these here on the right. This is the microwave background radiation as observed by the Planck satellite. The thermal relic left behind by the Big Bang from the epoch of recombination. So this is basically a signal we are receiving from all directions, and it's emitted just 380,000 years after the Big Bang. And at this time, the universe was very different from today's universe. It was very smooth. It had almost no perturbations in its density field. Apart from tiny little ripples that are imprinted on the density distribution at this early time. And that's what these satellite missions see. And you can then measure the angular power spectrum of these temperature fluctuations. This is shown here in this top diagram, or do, for example, cross correlations with the polarization signal, which is also observed. And the model that theory predicts for that under certain assumptions of the material content of the universe, namely lambda CDM, that's the blue line here. And you see that the data of Planck is, which are the red dots, is matching this theoretical model very precisely. And this is really the new situation in cosmology that nowadays it has become a precision science, not when compared to maybe fundamental physics measured experiments, but concerning the past, where uncertainties in even basic things like the expansion rate of the universe were factors of 2. We now know these things to % accuracy. We know that mean density of the universe to accuracies of 1% or so, and that all the other 6 numbers in total that describe the lambda CDM standard cosmological model are measured to that accuracy from the microwave background radiation, but also from lots of other cosmological measurements that all fall into places, that all support this comparatively simple model, lambda CDM. And I will talk more about this model and what it means. But one thing to realize is that at this early times, we can calculate things really well. This is basically linear theory, followed with Maxwell-Boltzmann codes that can be computed really accurately. But today's universe is very different. It is highly structured. We have, of course, luminous galaxies, each of them containing typically 100 billions of stars. And these galaxies, they come in different shapes and sizes. Here I've displayed a few of them. These galaxies here on the left, they have sometimes bars as the lower example, sometimes, and as in this hoax object, there's a ball of old stars surrounded by a blue ring of young stars, a very peculiar object. And then there are gigantic galaxies maybe up to 100 to 1,000 times more luminous than the Milky Way, sitting at the centers of galaxy clusters. Here on the right is one of them. These are the biggest galaxies we know, elliptical galaxies, very luminous and old objects, but they have also a maximum size, interestingly. And the density contrast in these objects is about 1 billion times the mean density in the center. So they are extremely nonlinear and certainly not something you can describe very simply, say with perturbation theory. You're far from this. And what we'd like to understand is how is this complex universe connected to the early state after the Big Bang, which we can describe somewhat more easily. And we know more things about galaxies. They not only individually about their properties, but also how they are distributed in space. Large so-called galaxy redshift surveys, they have mapped out what's called a large-scale structure in the universe. And you can do this by determining the position on the sky and the distance via the cosmological redshift of hundreds of thousands of galaxies. And once you've done that, you can draw them on a map, like in this pie diagram here, where this was done for about 100,000 galaxies. Every little yellow dot is a galaxy here. And if you do this, you obtain essentially three-dimensional maps of the galaxy distribution. And here we are sitting basically at the apex of this cone diagram. If you look out in space, you look backwards in time, up to billions of years here in the nearby universe already, and you see that the galaxies form a peculiar pattern. They are clumpy, they produce so-called filaments, and they surround large regions that are fairly empty, almost contain no galaxies. But that's the pattern of large-scale structure, which we also would like to understand. And now there's actually more. We also have galaxies in the very early universe. You can take telescopes, ideally in space, for example, the Hubble Space Telescope, and use them to expose for very long times. And for example, in this famous ultra deep field, Hubble was used to observe a black spot on the sky, seemingly a place where nothing was known. And by exposing for very long times, you then see and detect very, very faint galaxies that are very far away, in this case, about 10 billion light years away. And you can peel back in time to the birthplace of the earliest generation of galaxies, which you see on this image. Some of them, they partially resemble today's galaxies, but they are smaller, they are more lumpier, and they also have a different composition of shapes. So this young galaxy population was different than today's galaxies. And in astronomy, we try to understand, of course, how the galaxies have evolved over time to today's population. And so the type of work I'm doing is trying to essentially bridge the early state that we see in the microwave background with today's complex evolved state, 13.5 billion years later. So this is the time span that we would like to bridge in cosmic evolution. And in principle, the idea is very simple. We take the initial state and use that as initial conditions, and then apply the ordinary laws of physics and evolve that initial state forward in time. And if we do everything correctly, we should obtain today's universe. And that's fundamentally the idea. Of course, the details, as we'll discuss now, are difficult. But it's a compelling idea because the initial conditions here are actually precisely known in lambda CDM. There's really nothing that is unknown. I mean, we don't know the physical nature of the dark matter particle, for example. I'll come to this, but we can assume its properties, and in the default model, the properties are that of a non-interacting inert particle that's only following gravity. And if you make these assumptions, then all you need to know is the initial perturbation spectrum, and that's then precisely known and computable. and you have the matter content and its composition from the observations. And so you can realize the initial state with arbitrary accuracy in principle on a computer and evolve it forward in time. In principle, I say, because of course, there are many things where we have uncertainties, and I'll come to some of the astrophysical uncertainties later in my talk. So that's one thing. We have the initial conditions, we can realize them on the computer, and the question is what type of equations, what type of physics is it actually that we would like to compute forwards in time? And here it is primarily two systems of partial differential equations. Don't worry, I don't want to torture you with lots of equations in this talk, but just mention sort of what we actually try to number crunch on the computer. And the one system of equations is gas dynamics, classical fluid dynamics, because the baryonic gases, helium and hydrogen, that are produced in the hot Big Bang, those are initially filling the universe, and those gases have to be pulled into stars and then into galaxies. And fundamentally, this is a problem of fluid dynamics. So we solve essentially the Navier-Stokes equations, which are written here, just hyperbolic conservation laws for mass, momentum, and energy. And as you know, so fluid dynamics is a classical field, and it has its challenges even today. For example, turbulence, which inherently happens here. The topic of turbulence is still one that's actively researched. And in cosmology and astrophysics, we have lots of turbulence flows. They are happening all over the place, and the turbulence is also very, very strong. So you then already realize it's easier said than done, that the even hydrodynamics is actually in the nonlinear sector not that easy. But so that's basically for helium and hydrogen gases. And then we have a dark matter component in the universe, which makes up most of the mass in the actual matter sector. And of course, we don't really know what the dark matter particle is, but we think in the default model, it is a particle that is so weakly interacting that its interactions besides gravity can be completely neglected. So in that case, one describes that by the Pauzer-Vlasov system. This is simply the one particle distribution function of these particles in phase space, so the phase space density of the dark matter particles. And then you have a Poisson equation where this is coupled to the gravitational field. And this system of partial differential equations is six-dimensional, and it's time-dependent, and the high dimensionality of it, even though formally the equation doesn't look so hard, it's actually not something you can solve except for trivial cases. And that makes this field hard because we need to solve these partial differential equations on the computer, and that's what I will come to. And then, you know, this is basically the basics. And then if you want to have very sophisticated models, you also care about the radiation. So radiative transfer is another headache in this. Magnetohydrodynamics, we also do. And then close into black holes. You really care about, say, gravitational effects, gravitational fields that are so strong that the Newtonian gravity is not good enough. And then you need to invoke general relativity there as well. So basically, then so we have I've tried to describe that's the initial. We have an initial value problem. We have the partial differential equations. We discretize them, and then we try to exploit large supercomputers. Here's a typical image. You know, these machines are getting ever more powerful, but they are parallel computers. So we need to essentially devise methods to chunk our calculation such that each of these processes in these different racks can efficiently work on a little piece of the universe, so to speak. But then these pieces need to communicate partial results all the time with the other pieces. Gravity is a long-range force. And so our algorithms rely on fast communication. That's why we basically need these machines that have a very high performance backplane and can communicate a lot because of the long range nature of the coupling of each part via gravity. Basically, this is something that is relentlessly operating independent of distance, and that's cannot be neglected at any distance in the universe. So we have this problem that we have a tightly coupled problem to solve. Okay, now let me then come to more results of the calculation. So in principle, I already talked about this. The lambda CDM cosmology has this bewildering prediction or realization that was a major realization in cosmology, that we have this very strange matter energy contents today. This is the typical pie diagram that is always shown on these occasions, right? That the matter energy density today is only to about 5% composed of the baryonic material that we know from chemistry, and that is what we are really familiar with. And 95% is made up of two dark components. Dark matter, which is about one quarter of the cake, and that's this unknown elementary particle, presumably. At least that's the favored candidate. And then there is even a stranger component, dark energy, which only plays a role at late times, which is responsible for the accelerated expansion that we strangely measure over the last 5 billion years. So both of these components, as you all know, are mysterious still. There are many ideas, also some say exotic ideas what they really are. But here in this talk, I mostly talk about the really canonical vanilla model, where the dark energy is actually a cosmological constant in Einstein's theory of general relativity. So it is introduced as a cosmological constant that is consistent with all the data still. And we still don't have any evidence that's compelling that the dark energy is not a cosmological constant. So in some level, this is, by Occam's razor, probably still arguably the simplest model. Now, this is the real composition of the universe. But for a long time in cosmology, we actually could not directly study this on a computer in the nonlinear sector. We had to simplify this in the following form. We had to basically replace the baryons with dark matter as well. Then you get a fiducial dark matter only universe, which you see on the right. If you do this, then things are obviously much simpler, because we, in fact, exactly don't have to deal with the gas dynamics. We don't have to deal with any luminous stars either, right? All you then have is gravity driving the cosmic structure formation. And here, now I'm showing you a first movie, which I suspect will be very jerky on your end because of the Zoom connection. I apologize for this. These movies, if you're interested, you can also look up on our websites and then show in higher quality and its full glory. So, but I hope that you still see enough frames to get the picture. What this is showing is the structure formation process from basically this early time after Big Bang to today. What you see here is how in the dark matter structures grow hierarchically from small structures to large structures. The reason for this is that small density perturbations imprinted in the primordial universe, they are gravitationally unstable. They attract more matter because they are slightly overdense with time. And this process is initially slow, but then accelerates strongly. Such a perturbation decouples from the expansion of background space and then turns around and collapses on itself. And the dark matter there realizes it doesn't collapse to a point or into a black hole, because the dark matter particles can't get rid of their energy. They can't radiate it away, this energy either. There is no dissipative process. So what then happens is that the dark matter particles use the energy extracted out of the gravitational field and convert this to motion. And this motion then supports the virialized structures. And what you see here is a dark matter halo of a Milky Way sized galaxy. So this is really the theoretical prediction of what we think the dark matter structure of our own Milky Way should look like. And what you'll see, it's very lumpy. So it's filled with a sea of little dark matter lumps. And these are all structures that have fallen into this object during the structure growth period. And so that's very important, this prediction, because it helps us to understand where is actually dark matter to be found, for example, at the solar circle, and how lumpy is it? Where would we expect dark matter annihilation radiation, for example? This is another calculation that shows the dark matter structure today, and over much larger scales, over hundreds of millions of light years. That is the so-called cosmic web. That is basically what comes out of the evolution when you follow the dark matter forward in time and look at it today. And the dark matter forms a filamentary network. Along these filaments are different pebbles of different sizes. These are these virialized dark matter halos, the places where the galaxies form. And at the intersection of these filaments, you have particularly large structures. And actually, this visualization zooms in on a galaxy cluster that you see now at the center. And that's something the size of the Virgo cluster here. And embedded in it are about 1,000 galaxies. So this is something we can all understand very accurately these days. These calculations are more than a decade old now already. And all the codes nowadays, they all agree on this. And in fact, we can go further today. We can, in the dark sector alone, the cosmological simulations, they have become so good that they effectively can resolve all the structures that are expected down to the smallest dark matter objects that we expect. And in typical models where the dark matter is a WIMP, there's a thermal cutoff mass in the initial perturbations. So basically, the dark matter initially has some residual motion that smoothes out structures below that scale. That leads to the prediction that that astrophysically, the dark matter should produce only some halos up down to a certain size. In fact, this is about Earth mass for typical supersymmetric models that have been popular for a long time. And you see here a sequence of zooms in one of the modern simulations where we actually can zoom in all the way over about 30 orders of magnitude in mass to the smallest structures. These are, you see on the lower right. And at that point, the geometry of the web changes, and also the structures lose their self-similarity that is observed at larger scales. Because here you have then a physical scale imprinted where the initial power spectrum basically cuts off. So there is generically a smallest predicted size of dark matter lumps, here typically Earth mass. But in alternative dark matter models, this can be at another place. For example, there are so-called warm dark matter models, where the initial motions of the dark matter particles would be larger. They would be having a non-negligible thermal motion that's much larger, and then you basically push this mass scale to bigger objects. But this has very little impact on anything that's observable astronomically, which is a bit of a pity, right? We're trying, of course, to find observational signatures of this model, say a WIMP-like cold dark matter model versus a warm dark matter model. There is a lot of work in this sector done, which I have no time to review here today. Here, for example, one can then predict the concentration of these halos. This is important to make predictions for how much annihilation radiation you might expect from these dark matter clumping on different scales. So this is all, I think here these simulations are important to guide and help generate ideas for where to look for dark matter through various astronomical probes. And the field of astroparticle physics is, of course, doing this in many different ways. But let me now come really to the meat of my talk. Namely, this is about hydrodynamical simulations of galaxy formation. And this is really basically addressing the full problem. Here, we are not just trying to simulate the dark sector, dark matter, the clumping of dark matter, but we are really trying to see what are these 5% of baryons doing. And they will make stars and black holes. And you know, those are interesting. Evidently, these are the objects studied in astronomy, but on the grand scheme of things, the stars make up about a tenth at most of the baryons today. So then they would contribute about 0.5% to this energy mix. And black holes, they are about 1,000 times smaller still. So not a lot on the, we think, on the, basically in terms of total matter energy density. Even though one must say for black holes, there are also more exotic ideas. For example, there are still ideas discussed whether maybe primordial black holes could constitute part of the dark matter. Then, of course, this picture would change. But these black holes I'm mentioning here, these are the ones that we have astronomical evidence for, namely those in the centers of galaxies primarily, the so-called supermassive black holes. To simulate the baryonic sector, you also need special numerical methods. We are using here a technique that we specifically constructed, which uses a Voronoi tessellation of space. You see an example here in 2D. Basically, the reason the Voronoi tessellation is a geometric construction that you get from a set of points called a mesh generating points, and then you associate with the points that you throw in space always the spatial region that's closest to a given point. And then the boundaries of these cells are basically the orthogonal to the connecting lines of these points. Here you see now some of these cells marked up. And we use this these cells, this unstructured grid, as a dynamic way to follow the fluid motions. The hydrodynamics is best followed on grids, but Cartesian stationary grids are not very well suitable for the large dynamic range we encounter in galaxy formation, where the material is basically collected over large areas and then condenses into a galaxy. And what we like to have is to have high resolution in the centers of galaxies, and our mesh basically flows along with the material and creates this resolution right where we need it in the galaxies. And then it has other technical advantages having to do with the supersonic flows we have and so on. So that we've done, but in reality, we follow this in 3D, and we have actually tens of billions of these cells in our most modern calculations, just to give you a sense of the scope of it. Before I get to the result, just saying that in this baryonic sector, you now have to describe the physics of galaxy formation on top of just the fluid equations. And here there are essentially three main issues to address. One has to do with radiative cooling. This is relatively well understood. So you have, for example, the hot gas emits X-rays and cools. Because of that, this we have to model and include in our equations. And then there's a very difficult sector of once the gas cools and collapses under gravity and fragments to and gravity is very relentless. Once the gas becomes cold and self-gravitating, gravity will make any gas cloud fragment, and the fragments will collapse away until something stops it. And the first thing that is stopping it is then nuclear fusion in stars, and star formation is in that sense a subgrid treatment. So we follow the gas as it collapses to a certain point, and then we just have to say, based on semi-empirical laws, it's going to go to stars. That's what we introduce in our simulation. And similarly for black holes, this is something one cannot treat fully ab initio in a full universe calculation. You have to make very coarse approximations. Some of them I'll briefly describe later. And what we also recently were included are magnetic fields. They also play an important role, but are maybe not as important as these other three blocks. Now, having said this, let me show you a hydrodynamical simulation. This is one from our illustrious project. These are some of the most modern simulations of galaxy formation today. Again, I have to apologize if you don't see this movie in a smooth way. Here we first saw the dark matter, and in a hydrodynamical simulation, we not only have the dark matter, but we also have the baryons now. We can show the baryonic density, we can show the pollution with heavy elements that have been synthesized in stars, and we can actually see the stars that have been created in the simulation. And the zoom here ends close in to a galaxy that you see here. It's a disk galaxy, quite like our Milky Way. It's rotationally supported. It has blue stars because they are young. And the reassuring result of calculations like this is that if you really initialize the lambda CDM cosmology in a supercomputer and you put all of this baryonic physics in the equation that you study, and at the end of the day, you do get on the computer stellar distributions that look like real observed galaxies, and they actually have the same stellar mass and size as observed galaxies, then you cannot, of course, you are thinking that maybe we are on the right track after all, even though some details are not yet perfectly matching the observation data. And then let me come straight to some of the most modern results in this field. This is from our follow-up project. So this illustrious hydrosimulation. This was one of the very first large-scale hydrodynamical simulations of the universe that managed to produce real galaxies and successfully reproduce basic properties of them. And encouraged by this success, we have then in recent years produced a new set of simulations. It's called illustrious TNG, the next generation. And here we have simulated 3 cubical boxes of fiducial universes called 100 megaparsec on a side. So this is about 350 million light years on a side, 50 megaparsec on a side, and 50, 100, and 300. These are the 3 different boxes. And I'll show you a few results in a minute of them. And just to say that because of the richness of predictions these calculations create, they are very useful for astronomy and research in galaxy formation. You see this just alone from the impact these simulations have. We made all the data publicly available, and this has seen an uptake in the field that far exceeds our wildest dreams. Already more than 400 papers or so have been written on these simulations. Yeah, we are certainly proud on this. That's why I'm telling you that. But I think it shows that computational cosmology is really nowadays a main driver of this field, and it's making theoretical study in the nonlinear sector very much possible. These are the group of people, my collaborators, who were responsible for these simulations. And yeah, again, maybe I cut this short, but here we can then use these simulations to follow the gas flows in time, how they, for example, assemble a galaxy like the Milky Way. This is shown in this animation. This is a tiny cutout from one of our illustrious TNG simulations. And here in the big background frame, you see gas flows, and in the halo, you get a sense of the turbulence that's there. It's very difficult to follow this precisely. In the lower left, you see the dark matter component. That's basically in the same region of space as the cosmic gases. And in the lower right, you see the stellar disk that is formed, and also the cold gas in the disk. And now at this epoch of redshift 1.5 or so, this is about 5 million years ago or so. There you see already that the spiral disks have formed, and a lot of heavy elements have been synthesized in the stars of these disks, and they have been expelled over large regions of space by supernova-driven outflows that are followed in these simulations. Okay, then just to, and the important aspect of these simulations is now that they are trying to model a representative piece of the universe, not just a single galaxy. If we would only compute a single galaxy, we would, and maybe this would by chance match the properties of one of the hundreds of galaxies that are observed. Rather, the calculations, because they are following a representative piece of the universe, they produce the full galaxy populations. So hundreds, thousands, tens of thousands of galaxies, all of different shapes and sizes. You see here just a little inventory of a couple. So you have, all in a very narrow stellar mass range, and you see there are disks of different sizes. Here on the right, the stellar distribution. On the left is the colder gas in the galaxies. Sometimes you have spiral arm-like features and so on. And then what we do is we compare statistically whether this predicted galaxy population looks like what observational astronomers find. And we compare lots of different properties. For example, one important one is the so-called color distribution. So the stars, or basically the galaxies, come more or less in two different classes, a red sequence and a blue cloud. So the red galaxies, they have old stars. They don't have any ongoing star formation. The young stars are hot and massive and blue. And so in this top panel here, you see bimodality here. In the blue peak is the bigger one here. That's basically actively star-forming galaxies. And then there is a secondary peak on the right, which is the emerging red sequence. And as you go over these 6 panels, you go to galaxies that are bigger. And the bigger you go, the more red galaxies you have. So there is a transition between the blue cloud and the red sequence. And the astronomers call this the bimodality, here in the color distribution. And this dichotomy is very important in galaxy properties. And now for the first time, the simulation that we have actually produces this bimodality, which was an important success. Previous calculations have never obtained this. And I can tell you already now that the reason why we were successful here has to do directly with supermassive black holes. So that's what we basically compare. And then we use such a comparison to test and validate our theoretical ideas, how black holes influence galaxy formation. Use another comparison. The galaxy sizes different. They get bigger with more stellar mass. But again, there is a dichotomy. Disk galaxies and elliptical galaxies behave differently. And here again, we compare basically to observations to see whether our calculations make any sense. And the reassuring thing is that the agreement is actually relatively good, certainly better than we might have expected. And that's then the basis to look at further properties that are maybe more difficult to understand. So that's about individual galaxies, but the other area where calculations like these are very important nowadays is actually about the large-scale clustering and the large-scale distribution of matter and of galaxies. I alluded to this earlier when I showed you data on galaxy redshift surveys. Because the galaxy clustering, so the geometry basically of this web is still one of the most important probes for cosmology in today's universe. In particular, if you want to see whether the lambda cosmological dark energy, whether this is a cosmological constant or not, we have to also look at the late universe. We have to, because it becomes effective there. And there we have to look at galaxy clustering. And the question then is, can we in theory reproduce, can we understand from the theory point of view very well how galaxies are distributed in space today? And that's something that we need these simulations for to predict. And we then, of course, want to see how can they predict the success of the lambda CDM. And the answer is, it looks pretty good. I mean, at this point, that the large scale, the lambda CDM model is also doing here surprisingly well. Here you see data on the clustering pattern. This is measured here by, for example, a 2-point correlation function. We measure the access probability to find around a galaxy nearby another galaxy. The gravitational clumping basically produces a signal that's saying that the galaxies like to live together and they clump together. This clumping you can very accurately measure in the observations. For example, by the Sloan Digital Sky Survey, these are the black dots here in these different diagrams for galaxies of different mass. And then in red here is, for example, our simulation result. And this is something that we cannot tune in any way, right? This comes straight out of the simulation. And the agreement is good. It's not perfect, as you see here, in some of the more massive galaxies, but it's for us, it is reassuring that it's very close to what the data says. So, and that we all know from also other observations that lambda CDM is doing really very well. If the real universe has different physics, it is not easy to demonstrate it, right? So lambda CDM model is a good approximation for sure. Here is a clustering of red and blue galaxies separately, which also comes out in these simulations very well. Now, I mentioned, however, that this success, it has to do with supermassive black holes, and maybe this is the last topic I have some time to discuss today. And I first want to say something about the challenge that from the outset, if you try to simulate say a significant piece of the observable universe, but at the same time account correctly for the impact of supermassive black holes, you might think this is a hopeless task just because of the enormous dynamic range that you face here in a single calculation. And I try to illustrate this here. In the background on top right, you see in the typical large-scale dark matter simulation that basically, like the Millennium simulation that I showed earlier, that simulates a large piece of the universe. This you actually have to do in order to get the dark matter halos in which galaxies form correctly. This formation process is influenced by gravitational tidal forces, which are having which require relatively large volumes to simulate. So this is first of all what you have to have. But then you might want to zoom in into one of these dark matter lumps where the baryons are then accumulated and make a rotationally supported gas disk that is cold, and in this cold gas disk, the baryons under self-gravity collapse further, fragment, and then collapse all the way to stellar densities until fusion ignites in the stars, and at that point the stars will stabilize and shine. And when they shine, they emit a lot of energy, hard radiation, and they emit mechanical winds and so on when they interact with the environment. That you see in this disk side, seen here from the side edge on. This is the interstellar medium in a typical spiral disk galaxy. And this interstellar medium is highly turbulent. It's highly turbulent because all the stars that have formed there constantly inject a lot of energy through the emission, winds, radiation, but also through supernova explosions that go on here. And that's a process we have to somehow model in the calculation. And of course, these are already tiny scales compared to this background. But what's worse is that at the center of the galaxy, you have a supermassive black hole. Our own Milky Way has one, of course, as well, Sagittarius A star. And these supermassive black holes, they have masses between 1 million to 1 billion solar masses. They sit at the centers of these galaxies, and occasionally they are fed by gas streams that flow into the galaxy. And this is here enlarged. This is an accretion disk. This accretion disk, if it exists, is about the size of the solar system. Very, very small compared to the galaxy itself. And that is what I like to call the dynamical range challenge. The coupled evolution of supermassive black holes, galaxies, and the dark matter in cosmology is a physics problem that is just coupling many different scales together. And we have the problem that we can only, even with the best codes, not do this in an ab initio way, because we can only simulate a range of scales at any given time. And whereas we certainly can claim that all the physics that is potentially relevant is included all the time, right? We have cosmic rays, for example, or even neutrino physics is usually neglected. And then the crux is that, and that makes this field difficult, is that you cannot just say, let me forget about the black hole, ignore it. The problem is that this tiny black hole at the center is still affecting the whole galaxy. And that's what I will talk about now. Because supermassive black holes that sit at the center of galaxies, they are incredible engines. And they liberate incredible amounts of energy when they grow. When they are fed with gas flows, that then they can shine for some 100 million years or so as brightly as the whole galaxy. That is called a quasar or active galactic nuclei. So AGN is here the acronym for active galactic nucleus. And when such a quasar shines like as bright as 10 to the 12 stars, for say 10 to 7 years or so, then it liberates about 10 to the 60 ergs. That's about 1 billion supernova explosions. So it's an enormous amount of energy, and that energy is basically appearing in a point-like region in the center of a galaxy. And the issue is, what does this energy do? How much of it does couple to the galaxy and then affect its evolution? One can also compare this energy to the total energy released by all the supernovae combined in the whole observable universe. And if you do that exercise, you find that all the quasars combined over the lifetime of the universe liberate about the same amount of energy as all the supernova explosions combined. That already shows you maybe that both of these energy sources, they are really decisive in regulating star formation and galaxy growth. And one picture, for example, is that when two galaxies collide, you see a time sequence of an old simulation we've done also more than a decade ago. Here are two spiral galaxies. It's a time sequence here. When they collide, they have supermassive black holes at the center. First, the galaxies will pass each other, and then gravitational tidal forces, they drive gas in the center where the black holes are, and then the quasar starts shining, which is sort of illustrated here with this yellow spot. And this energy input will then expel the rest of the gas that's in this galaxy, and then the material that's available otherwise for star formation is then gone, and then the galaxy will become a red galaxy. And so here you basically see the basic picture that maybe black holes have something to do with the transition of galaxies from actively star forming, from bluish systems to red systems. And this is sort of an idea that has gained a lot of traction in the last decade. All the simulation groups in the world now try to use that picture to produce the red and dead galaxies in the universe that we see. And yeah, I skipped this detail. And yeah, unfortunately, I have another really nice movie that shows you now the gas flows with the black holes embedded in the background. And yeah, I'm a pity that you don't see this really smoothly, probably over Zoom. But here at the bottom, there's a little object, and it starts black hole activity now. So what's so red and violent here, this is the velocity field of the cosmic gases over a large region of space. So you get a picture here of the turbulence in the intragalactic space. And here from the right, there will be another galaxy moving in where a black hole is triggered, accretion on the black hole is triggered, and it starts growing, and then you see these large-scale outflows. These are basically bimodal winds that are emanating from galaxies. And we think nowadays that really supermassive black holes during the growth process, they are responsible for transporting material that is from the innermost regions of galaxies to the outer regions. And now the movie here has transitioned to actually the stellar distribution. So this is what you see here in black and white. These are the stars in a forming galaxy cluster now. And all of this black hole activity that you saw in the beginning, this is sort of co-spatially taking place here. And we think that the central galaxy in this galaxy cluster will be essentially switched off by the energy input of the growing black holes. So I maybe say one more little point about whether this picture is at all correct. So I stressed a bit that some of these calculations cannot be done fully ab initio, especially with respect to the black hole physics. So the growth process and also the way that the black holes liberate energy locally needs to be very closely parameterized. And then that begs the question, of course, are these results, any good? Are they reliable or not? That is, of course, a $1 billion question. We are trying to prove that or understand to what extent they are not by doing, of course, locally better calculations in the future and with more physics very close into the black hole. This is one way to go. And the other is also to check whether the predictions these calculations create, how the galaxies are basically switched off by black hole energy, whether this is seen in the data. And here I want to just show you two recent results from last year where we made such comparisons. One is basically comparing to a survey with the Hubble Space Telescope, stacked images of galaxies where you can demonstrate, and I'll cut it short since most of you are anyhow not experts in these astronomical observations. But what this picture basically shows is that the galaxies that stop their star formation, they do this from inside out. So it is like a wave that's propagating in this galaxy from the innermost region to the outermost region. The star formation is progressively switching off. So this is something we also find in our simulations. And we attribute this to the action of the black hole in the center of galaxies, that it's basically doing its damage first at the very center and then progressively further out. So this is basically shown in these comparisons with these stacked images of HST. And then recently we had a Nature paper last year where we showed that another interesting finding, namely something in the observations, first of all, that if you look at many thousands of disk galaxies in our local universe, so you have these disk orientation, and then in this galaxy there are typically satellite systems. In our own Milky Way we have this too. We have, for example, the Magellanic Clouds. And then you can ask the question of whether the star formation activity of these satellite systems is somehow correlated with the place in which they are in this galaxy relative to the orientation to the normal vector basically of this disk. And it turns out that in the data there is a weak modulation of all the satellites, namely that along the major axis on the disk plane, the satellites, they tend to have less star formation. They are already they are more quiescent, as we say. They are more quenched already in the disk plane here. And the question then was, where does this come from? And we compared this with our simulation model, elasticity G, and this is shown here. The green line, we see exactly the same modulation as seen in the data. So that's interesting. So I have this effect. But this is completely gone if we simulate without supermassive black holes. So we have also done this. This is something you can do with these calculations. You can do hypothesis testing. You can, for example, run a galaxy formation simulation without supermassive black holes, without their energy input. Then you get different outcomes. And turns out, for example, these supermassive black holes, if you omit them, you do not have this. You do not have this modulation. And we argue that this is coming from ultimately a modulation of the gas density in these halos. The black hole that sits at the center is, through its winds, bimodal outflows, it's creating a low density region basically on top and the bottom of this disk. And in these low density regions, infalling satellites, they are experiencing less ram pressure stripping, and then they can form more stars. And so that modulation in the density is actually enough to explain this effect. And we then use things like these to indirectly validate our modeling. I think I'm basically at the end of time. I should come to an end. So I could, if I would have been better in keeping time, I could have talked about magnetic field predictions, which are also very interesting. We do this. We can predict magnetic fields nowadays in the galaxy. They come out quite in good agreement with observations. There are small-scale dynamos that make these fields independent from very tiny seed fields. And in current work, we are trying to make the physics more realistic by also accounting for so-called cosmic rays. So energetic protons, relativistic protons that are coupled to the gas through scattering on Alfvén waves, and they exert also pressure on the gas in our Milky Way. And we think that these cosmic rays are also a driver of flows in galaxies. So there's a lot of active work in the field trying to understand this. And with this, I want to rather come to the end because I think time is pretty much up. So what I'd try to summarize in this overview talk is basically a little bit the field of hydrodynamical cosmological simulations. So they are nowadays, I think, a very powerful tool to to predict the nonlinear outcome of this, if you think about it, rather strange hypothesis that the universe is made up of dark matter and dark energy. And I think without these simulations, if they wouldn't confirm that this weird mixture actually produces structures just like the galaxies we see, we probably would have less confidence in astronomy that this is a viable model. Nowadays, I would say there are maybe two directions in the field. One direction is that we try to use these calculations to support the work in cosmology to really find cracks in lambda CDM. Is there evidence that dark energy is not a cosmological constant? For example, a question, is there evidence that dark matter is not cold dark matter particles, something else? So that's one area where the simulations are very much needed. And the other area is actually understanding the physics of galaxy formation itself. So this is what I talked about at the end. Are supermassive black holes just an interesting side phenomenon in galaxy formation, or are they an active player? Are supermassive black holes really shaping the properties of galaxies? And at the moment, we actually think it's the latter. Black hole physics and galaxy formation physics are actually intertwined, and we can understand them not separately from each other. So thanks a lot.
Many, many thanks for this beautiful colloquium, also visually. I could see the videos perfectly, so I hope everybody else could as well. So we open the floor to questions, and please raise your hand in case you would like to ask questions. So Ludwig.
Thank you very much. I'm really impressed by the accuracy of this skeletal classical physics to predict, to reproduce our universe. But my question is, did you try to extrapolate in a few billion years ahead? What will be the future of our universe according to this simulation? Just a few billion years only.
Oh yeah, thanks. This is a very very interesting question. We have done this not with this illustrious TNG simulation I talked about, because that was very expensive to compute. I haven't mentioned this, just to give you a flavor. These are several tens of millions of CPU hours that we used for those. So running into the future, we haven't done this there, but we have done this for smaller calculations in the past. In the lambda CDM cosmology, what will happen is, or what happens there generically, is that the structure formation freezes out. This is something that already takes place now, because the expansion rate is now accelerating. That's coming from the cosmological constant. So the universe is basically going into exponential expansion again. And what this produces is that in linear theory, the growth actually halts. So the structures that have formed, they stay and they manage to still grow a little bit, but by swallowing basically nearby matter. But after that, the structure formation really stops. So the dark matter halos, they don't get bigger anymore. Their separation gets ever bigger. And in lambda CDM, what you will end up with is basically that these structures that have already formed today, they stay around, they grow only a little bit, and then they spend the rest of eternity more or less alone. And in the lambda CDM cosmology, the structures are not ripped apart, despite the fact that space ever comes bigger and bigger. So they will become, however, isolated, and because of relativistic effects, our so-called horizon shrinks and comes ever closer to us. So we will then, in the far future, not be able to see very distant galaxies anymore. In our own galaxy, we will basically become isolated from the rest of the universe with time. And the dark matter halos, they will just relax, get ever rounder with time. They become more spherical with time. The star formation rate continues to decline. I should say that already the activity of our universe today is about a factor of 10 lower in star formation density than it used to be, right? So universe has been very active 5-6 billion years ago, but now it's aging. Our universe is getting an ever more boring place if lambda CDM is correct.
Thank you very much.
Augusto.
Yeah, thank you. So I was very impressed by these simulations. When you zoom in down and you see the spiral galaxy, and if I gather correctly, you go to smaller scales and even smaller galaxies like globular clusters and distributions of globular clusters and dwarf galaxies are well described by your simulations, if I understood. And then the question is, are you planning to zoom in more and see planets around stars? And what are the prospects?
Yeah, that's a great question. So, I mean, you're right. I mean, at the moment we are able to zoom in to a certain degree, but there is, you saw it some in my movies. If you keep zooming, eventually you see only a blurry thing, right? So there is a lower resolution limit. There is, we call it a subgrid or something, always in these simulations. So you have a certain information content. And then what we can try, I mean, we've done this in the dark matter case, that we have nested, we have repeated the simulation by putting at a certain spot much higher resolution. We call this a CERN calculation, right? We have this large region of the universe, and then we simulate it first once, then maybe we pick one interesting galaxy and you would say, this galaxy I would like to see with more detail. What we can then do is we can repeat the whole thing again, but at the place where the galaxy formed, basically put in a final grid, if you want, right? We increase the resolution locally. And if you like, you can repeat this process multiple times, and then you can maybe in a tiny, tiny volume, like with a microscope, you're trying to get more detail there. This is, yeah, but it's really difficult to make several of these steps and planet formation to come to this point. So we at the moment, our level is, we can go down in the best zooms we have done to individual stars, basically. So we can reach the resolution that in most of the simulation, I've showed you the stars that I called star particles. They're really actually balls of stars. They're not individual stars, okay? But we can go to individual stars. But going to planets is still, I will not see in my career for sure. So it's so difficult. It will not happen.
Thank you.
George Smirnov. Hello?
I think you're muted maybe, or no. I can't hear you, George.
No, George Smirnov, we cannot hear you. Okay, I think we go to the next George Sabidi.
Hello, thank you very much for interesting talk. I would like to ask you, there was a simulations which you show was a n-body simulation, and then with the partial differential equation. You want to say that they are consistent? That's my first question. And the second is that supermassive black holes, did you really got in the simulations, or it was embedded by hand? Thank you.
Yeah, thanks. Yeah, very good question. So the first question is you wondered about the numerical method for discretizing basic partial differential equation. For the dark matter, indeed, I mean, we're using basically a Monte Carlo approach to sample the phase space with particles. So the dark matter is represented by an n-body method and not, say, in a continuum representation. There's lots of arguments back and forth, you know, whether there are differences to a continuum solution to the, say, the Boltzmann equation and the Poisson equation or not. So, but to be clear, yeah, the dark matter was represented as an n-body system with tens of billions of particles, so relatively finely sampled, but still a Monte Carlo sampling. And for the gas, it was a continuum representation, discretization of these equations. Now, the black hole is not forming, so what we actually put in is what we call a seed black hole. So we are not able to actually clarify with these simulations the ultimate origin, or where the black hole comes from. We have to put in a black hole of a small mass as a seed, and then we can study basically how it continues to grow under gas accretion and mergers. But this initial formation of the basic, either it could come from a dying star, or it could come from a collapse or of a huge cloud, that we don't follow in these calculations. So it's basically put in by hand, the seed black hole.
Thank you very much.
Davidson.
Can I ask question?
Sorry, George Smirnov. Yes, please, go ahead.
Sorry for the delay. I have a technical question related to the simulation technique. I presume you don't have an infinitely power of computers. And you have mentioned the issue of dynamic range challenge. So indeed, in the simulation, you deal with very small and extraordinarily high numbers, numerical numbers for meta density, for distances and time. And this can cause huge problems with numerical accuracy. So is there anything you sacrifice in calculations?
Yeah, I think I know what you are driving at. We have, for example, numerical round of errors, and you have to be very careful to for loss of precision, for example, if just the way you represent physical quantities, so that you don't have overflows, underflows, and then you have loss of precision. You have, of course, we have very chaotic systems. Some of these nonlinear dynamics is very prone to be influenced by small, details, truncation errors, and so on. And then, for example, the orbit of a single dark matter particle, right? We have maybe 20 billion of these particles. If you ask, and fundamentally what we do is we integrate the orbit of such a particle, right? And the question is, now if I change maybe a small detail in my code, will the orbit be exactly the same? And the answer is no, it will typically not. So if I make a round of error somewhere, that can get amplified, and eventually there's the Lyapunov exponent in nonlinear dynamics and so on. So we have all of these effects, but they're also very strong attraction. So what we find is that many of the systems themselves, they show very strong attractor-like dynamics. So for example, when you have a dark matter halo, will be an n-body system of maybe 1 million particles. Even if you cannot follow every single of these 1 million particles exactly the same, if you change the time stepping and so on, their orbit might deviate, but the collection of these particles is completely robust still. So that's what I think rescues this. So the insensitivity to, for example, numerical round-off is much reduced by that. The other issues, we of course have to have, we need to know where we need double precision, where we need, where can we maybe use a more compressed storage. All of this is our daily bread and butter. And I cannot guarantee you that we don't make mistakes here. That would be ridiculous, right? We're trying to avoid mistakes, but it's a difficult business.
Davidson.
Well, hello, I have a very naive question that's maybe silly. Suppose I wanted my cold dark matter to be a QCD axion. I think I can describe it as a fluid. So could you turn off your cold dark matter and put an axion instead?
Yeah, that's not a stupid question. I think it's a very interesting question, I find. Axions indeed is actually something we investigate already. The very light axions in particular. In the field, we talk about fuzzy dark matter or quantum wave dark matter, because a proper description of that, as a fluid there is, then you can take go to the non-relativistic limit of this, and it basically in some typical limit, you end up with basically a Schrödinger Poisson system where then a wave function is actually used to describe the density of the dark matter, coupled to a basic self-gravity. And what you then this type of dynamics is very interesting because it produces on large scales exactly the same dynamics as our traditional cold dark matter scenario, with the only on small scales, on the scales of the de Broglie wavelength, you then get basic quantum effects. There is there are interference patterns even, so there are order of unity fluctuation in density and depending on the mass of your axion, this length scale can reach the size of galaxies. And you know, I think this is getting more and more, at least in my field, this idea that the dark matter could be an axion is actively investigated and is taken quite seriously. It's still it's at some level you could say a non-standard model, but because of this fact that on large scale, so with an axion dark matter, you can make all the large scale structure stuff that I described. You can reproduce just as well. And the question is whether on very small scales, the particular axion dynamics, the quantum effects, whether they are visible somewhere, right? And actually, there are these solitonic cores, Bose-Einstein-like concept at the center that makes, you know, maybe the rotation curves of galaxies even better for more consistent data. That's also why astronomers are fascinated that this could be a possibility. Unfortunately, simulating this is hard. We can't just put this into our standard code, because you actually, to do it properly, you have to represent the dark matter with this wave function and not with dark matter particles. You know, the Monte Carlo sampling of the collision-Boltzmann equation is not good enough for that. And I have a student actually working on this at the moment. So it's, from the technical point of view, it's relatively hard to do this. But several people around the world trying to do that.
Okay, maybe one question: how sensitive are you to the exact composition of the cake? So the fact that you have 26.8% dark matter and 68% dark energy. If you change those proportions, what would happen to your simulations? So
yeah, that's right. I mean, exactly. I mentioned in the beginning the precision. You know, would we, if it slightly change the dark matter content, or maybe increase it by 5% or go down by 20%, would galaxy formation substantially change? And yeah, qualitatively, not really. I mean, you have to make drastic changes. So if you, for example, omit the dark matter, or if you reverse the ratio, if you, for example, make the baryons dominant and the dark matter subdominant, then that is completely excluded. I mean, we have run such simulations in the past. You just can't get galaxies like the ones we know. That's also indirectly, you know, one of the, to me, always strongest arguments for dark matter. You know, if you just can't omit the dark matter and get structures that are plausible, right there. That's one thing. But unfortunately, you cannot use galaxy properties really easily to infer the exact you know, to 1% dark matter density. That's too insensitive. You can change the dark matter density by quite a bit before the galaxy properties are really very different. Yes.
Thank you. So I don't see any other questions, and it's already 5:45. So many thanks for this brilliant colloquium, and okay, thank you again. Bye bye.
Bye bye.
Bye bye.
Bye.